I'm Becca, and this is my motion of a falling object lab. So, a quick introduction. The purpose of this lab is to observe and analyze the motion of a falling pickleball. I will use a computational model to simulate the real motion of an object and determine if the pickleball ended up reaching terminal velocity. Some basic models used will use Newton's second law as well as the momentum principle, which states that momentum is equal to mass times velocity, and the change of momentum, also known as impulse, is equal to the net force times delta t. Because the mass of the pickleball is unchanging, changes in velocity will be caused by a net force. The net force is equal to the force of gravity plus the force of drag. We will also use position update and velocity update formulas for our coding, which are just rearrangements of Newton's second law. We will also use this formula shown here to the right. A quick preview of results. So both gravity and drag are observed to be forces acting on the ball, as predicted by the computational model. Drag is in the upwards direction and gravity is in the downwards direction. Terminal velocity, where drag and gravity are canceling each other out, is not achieved by the pickleball during its descent. The system in this lab will be the pickleball, and the surroundings will be earth, floor, and air. Earth is responsible for the force of gravity, and when the pickleball's speed increases, there is also an increased force and drag upwards on the ball. Initial conditions. The pickleball is dropped from rest from 1.676 meters above the ground. The mass of the pickleball is 0.024 kilograms, and the origin is located at the floor, lined up with the motion of the pickleball. We will assume that pickleball is point mass measured from the middle of the pickleball, and drag force acts akin to the equation described, proportional to the square of the velocity. So again, the pickleball is dropped from 1.676 meters above the ground and lands on the floor, which is the origin in this case, so it is observed to move in the negative y direction. The time of the fall from release to hitting the floor is 0.512 seconds, and here's my video. So usage of Newton's second law. We'll use velocity and position update formulas, which are derived from the momentum principle. We'll also use the impulse formula, which is shown here at the top. And in this lab, we can assume that the average velocity is equal to the final velocity because there is a non-constant net force. So by iteratively repeating these formulas, I constantly update the pickleball's position and velocity, revealing its changing motion over time. I will use small steps to achieve convergence. So details of coding. I first created a gravity-only program. I set the ball's mass equal to 0.024 to account for the pickleball's mass, and I set the ball's position equal to the vector shown, and I changed in the y direction, I changed for that value to equal 1.676 to account for the meters above the ground that the pickleball was dropped. I changed delta t to 1/60 because that is what tracker said, and I set b equal to 0 because there's no drag in this program. I changed t to the fall time, which is 0.512 seconds, and F net in here is just the force of gravity, so it's mass times gravity times the y-axis. And I set the velocity equal to the velocity update formula and the position equal to the position update formula, and my graph is shown for this program. I then ran a gravity plus drag program, and I changed b, the proportionality constant, to 0.01, and now there is a force of drag. The force of gravity is equal to the negative value of mass times gravity times the y-axis, and the force of drag is equal to the proportionality constant b times the magnitude of the ball's velocity times the magnitude of the ball's velocity times the y-axis. And then the net force is equal to the force of gravity plus the force of drag. And for this program, my graph is also shown. So I then created a graph that included all three models, the gravity-only model, the gravity plus drag model, and the observed position model in tracker. And as you can see, the gravity plus drag model and the observed position in tracker model are almost identical. They're almost overlapping the entire time of the graph, and the gravity-only model is a little bit off. It is assuming a little bit more motion there, and it's a little bit below the other two. Discussion of results. The proportionality constant b found to be roughly 0.01 through trial and error. Without gravity, the change in position versus time goes below 0, approximately negative 0.08 meters, whereas the accounting for drag creates a model very similar to the observed motion in tracker. The lines overlap for the most part. This difference is explained by the momentum principle. Because not all net forces were accounted for in the gravity-only model, the velocities and positions were changed. By accounting for all forces, we get a much more accurate graph. Some possible sources of error. There may have been misplacement of coordinate axes in tracker. If the ball's height was mismeasured, then its change in momentum also will be measured incorrectly. There is possible twisting of the ball. When measuring from the center, there is the possibility of not accounting for movements of the ball that differ from just straight down. So what does it mean in terms of terminal velocity? If terminal velocity is achieved, then the velocity is not changing for any object because the two vertical forces, drag and gravity, on the ball cancel out for a net force of 0 due to the momentum principle. Thus, terminal velocity will be represented by a flat straight line on the graphs of velocity versus time. As you can see to the right, neither model represents terminal velocity. What if the ball was thrown down? If the ball was thrown down, our new code would start velocity as a negative value, and it would be negative 10 meters per second in the y direction. The new graph from gravity and the drag model does not show terminal velocity. As you can see to the right, terminal velocity does not depend on initial velocity. Conclusions. The significant forces acting on the pickleball during its descent were gravity and drag, as seen by the similarities between that computational model and the actual motion of the pickleball. Terminal velocity is not achieved by the pickleball in its descent, and it would not have been achieved by starting the pickleball with an initial downward velocity. Thank you.